Good morning. This week's lab, we are looking at polarization. Now, polarization may take us back a bit. I think we've already done one lab where we worked with these microwave transmitters and receivers in terms of interference. But now we're actually going to look at polarization. And polarization was presented back in chapter 35. Kind of at the end of the chapter, and it has to do with, it actually traces back to the spin of the photon. Spins can actually be in one of two possible spin states, and quantum mechanics says that we can represent those spin states as different types of bases. So let's talk about what that means. So first of all, let's introduce some of the, or reintroduce maybe, some of the items here. So here's our microwave transmitter. So we're going to be powering that up. We're going to plug that in. Now it does turn out that you can look and see kind of into the transmitter itself. The microwave photons that are being generated are actually being generated from oscillating currents inside here at a very particular frequency. And so we can control what the wavelengths are, we can control what the frequencies are by controlling the circuit properties. Now, the way this is generated is it's generated with the electric field varying only in the vertical direction. So our transmitters are generating polarized light. Now, it's not in the visible part of the spectrum, it's in the microwave part of the spectrum, but it's polarized. So what that says is, and as long as we've taken a look at the transmitter, let's take a look at the receiver. So the receiver looks like this. It looks a lot like the transmitter, except that in this case, what the receiver does is if there are electric fields around, the transmitter will, or the receiver will generate an electric current. And so it's going to tell us, it's going to measure the intensity of the light coming in of the microwave photons, but it's going to do that, here it has it listed as microamps. So we're just going to call these intensity units. So we're not going to be very particular about what the units are, and there's even some calibration effects that you can control here. So these are just going to be an arbitrary intensity units, but that's what the receiver looks like. Now, let's see. So here's the transmitter. We're going to do two different types of setups. It says here that, I don't think that's how you measure is spelled with an E on the end. That looks better. Measure the intensity of polarized light as a function of some kind of a rotation angle. So the idea is this. The transmitter is set up so that it's only generating vertically polarized light. There's nothing in the horizontal direction. The receiver is also set up so that it only takes in vertically polarized light. Horizontal polarized light does not generate a current for this. So kind of the antennas that are being used to generate the light, the microwave light, and absorb that are vertically oriented. So what that says is, well, what happens if I have a transmitter that's generating light that's only vertically polarized? Well, what happens if I rotate the receiver? Well, as I rotate the receiver is going to become less and less effective at picking up that vertically polarized light. In fact, by the time I've turned it 90 degrees, if this is perfectly polarized in terms of generating the light and perfectly polarized in terms of the receiver properties, at 90 degrees it won't register anything at all. So what we're going to do is we're going to rotate the receiver. Now when you think about this, I could either rotate the transmitter or the receiver. I just need to get a relative angle set up between the two. And we want to take that all the way around from 0 to 360 degrees. We want to map this out. And so we'll be collecting a good amount of data on this. And, well, let's take a look and see. When we talked about polarized light back in chapter 35, we said that, let's go back even farther. Let's go back to physics 4b, or physics, earlier in physics 3b, I guess. Let's go back and take a look at light. And we said that if light's heading in some direction, that the individual photons have their own little electric and magnetic fields, so they can interact with other particles based on those electric and magnetic fields. And everything is mutually perpendicular. Now, what we also learned back in chapter 31 is when we're looking at these long-distance photons, the light that we looked at in chapter 31 was different from the electric and magnetic fields that we had looked at in previous chapters. In chapter 31, when we're looking at the electric and magnetic fields, they were specifically the electric and magnetic field of light that's propagating some distance, stuff that's being sent from a radio station, or something that's communicating through your cell phones, something like that. And so if we pick a direction of velocity, well, if I know the direction of the electric field, I can always determine what the magnetic field direction is. So I don't need to keep track of both. So let's just ignore the magnetic field. Now, what that does, though, is it shows us that if we pick the z direction to be a coordinate system where the velocity is in the z direction, then the electric field could have components in the x and the y. As long as it's perpendicular to the velocity, the electric field is allowed to have components in either of those two directions. So again, if we think of this as the photons are coming out of the board in the z direction, then I could have electric field components in the x and the y in general. Now, if I have both of those, and I have them set up with kind of a random phase between them, that's what we call unpolarized light. Now, the interesting feature of this from quantum mechanics is that it's not that the different photons have different polarizations to them, it's that each individual photon hasn't made its mind up yet. It's leaving its options open. It's going, do I want to be horizontally polarized, or would I prefer to be vertically polarized? I just don't know. I'm waiting until I run into something, and then I'll have to commit. So if we start out with these photons as unpolarized photons, they haven't made their minds up yet about which polarization they are, then we can represent it this way. Now, the setup we have, the photons have already been determined. So these are not unpolarized photons coming out. They are polarized. They have been generated with a very specific direction for their electric fields. And so for the transmitter photons coming out, we're going to represent it as having an electric field only in the y direction. Now, what happens when photons that are polarized in the vertical direction, what happens when they run into a receiver that's rotated through some angle? Well, the photons have to recalibrate. They have to go, okay, let's see, I was vertically polarized, but now that I'm running into this receiver at a different angle, I have to think in terms of components. Okay. Now, let me switch this around for a minute. Let me take the receiver and bring that back vertical. We said that the only important question here is what's the relative angle. So I'm going to try thinking about, well, how would we think about this if we rotated the transmitter? Well, if I rotate the transmitter, instead of the light now being vertically polarized relative to the room, now the light is polarized at a particular angle. So this is like the light reaching the transmitter for reaching the receiver, for the setup that we currently have. So if the light's coming in at some angle, but the transmitter is saying, no, I'm only going to accept vertically polarized light, what we can do is we can divide the light up actually into components. So we can say, now in linear algebra, this is related to the ideas of a basis set of functions. Now here the basis set only consists of two possibilities. What we're saying is it's either x or it's y. So I can take this quantum state that this photon is in and then move it to a different basis where it's either x or y, and then we can determine what the components will be. So what we've learned back in, again, chapters 34 and 35, kind of the quantum optics, is that the intensity that we measure is proportional to the amplitude squared. Now, the stuff we learned back in chapter 31, in terms of electric and magnetic fields, the electric and magnetic fields are proportional to what we're now calling the amplitude of the photon. So if I square that, what's going to happen is the receiver is not going to pick up the sine theta component. That's not going to be absorbed. The receiver is not capable of absorbing that. So it's only going to pick up an e cosine theta component. So what that says is the component that we pick up will only be the vertical component, and that's going to give us an intensity of the receiver. The receiver is going to measure an intensity that's only cosine squared theta. Now, again, in quantum mechanics, we're saying the photons haven't made their mind up yet. And so this factor becomes a probability. What's the probability that a photon with this polarization will end up in a vertical quantum state? And the probability is cosine squared theta. What's the probability it ends up in a horizontal quantum state? Well, that would be sine squared theta. So those are the two probabilities. And since the receiver can only pick up the vertically polarized photons, the intensity we measure here will be the cosine squared theta portion of that. All right, so we're going to get these data tables. We're going to take measurements every 10 degrees. I haven't decided which we want to try now. Do we want to try rotating the transmitter, or do we want to try rotating the receiver? But we'll put together, we've got to generate some data tables for that. Now, that's the first method we're going to work in terms of. We want to try a second method also, and that's one where we imagine leaving the transmitter and the receiver oriented so that they line up with each other. But what we're going to do in between the two is we're going to place a polarizing material. Now, as the photons come through this region, if we put some conductive material in there, that enables the photons to be absorbed by the electrons in this material. And if we put lines of conducting material, then the electrons can actually absorb those photons. So if I place this plate in a horizontal orientation, that's going to take out any horizontal polarization that we have. So what we can do then is I can take this polarizer material and I can rotate it. So this time we're going to rotate the polarizer material 10 degrees at a time. We'll put the polarizer in the region between the transmitter and the receiver. So let's just try a couple setups. First of all, let's go back to setup number 1. So in setup number 1, I'm going to power up my transmitter. Look, that scale, if you remember looking at the receiver, that scale has jumped off scale. I got to adjust it back down. It's reading maximum intensity, 50 intensity units. That's as high as these things go. So I've got a 50 at the peak value here. Now, what would happen if, well, let's try the transmitter. So I'm going to take the transmitter now, and I am going to start rotating it. You know what's happening to the intensity over here? It's dropping down. So the intensity is dropping down. Now, again, we said that if these are perfectly polarized in terms of transmitting and receiving, then at 90 degrees it should go to 0, and yeah, it really did. So these are pretty distinct polarizers, or polarized light for these devices. So yeah, I'm definitely seeing that polarizing effect. Now, just because it went to 0, does that mean that it's following this function? Not necessarily. So that's what we're going to map out. We're going to do some graphs. So here's the graphs on that first part. And what we're going to do is we'll do the intensity as a function of angle. Here we are going all the way from 0 to, oh no, I did two graphs, I did the wrong one. So I think the data, let me talk about this lower one. So I scaled this from 0 to 360 degrees. I am collecting data 10 degrees at a time in terms of rotation. Now on these graphs, and I know I've made comments on lab reports already, the data, you've always got to show your data prominently. Don't not show the data. The data is the most important thing. So once you got the graph set up, you've got it scaled properly, and it looks like maybe the peak values here are going to top out at 50 or something. The data is the most important thing. So make sure your graphs are labeled and that the data is plotted very carefully and correctly onto that graph. Now, in today's lab, instead of having like an accepted value, we're going to work from the theoretical formula that we've derived. So the idea is that we'll have a theory curve. Now, you can play around with whatever application you're using to generate these graphs. Some applications will allow you to go in and put in a function. If that's possible, I would say go ahead and put in the function cosine theta. Now there's a trick you can use if the application you're using to generate your graphs is not allowing you to put in your own function. What you can do is you can send it a bunch of theory numbers. So let's say that you send in a bunch of theory numbers, and then you can tell it not to show the data points, but instead show a trend line. So if you send it in a bunch of numbers by following this formula in terms of theta, and then what you could do is you could generate a trend line. So either directly put the function in or generate a column of numbers that have a column of theory numbers, and then use those to generate a trend line, okay, for comparison. What we want to be able to do is compare a theoretical curve with the actual data points that we are measuring. Okay, now that is all for setup number 1. Setup number 2 that we were just talking about involves leaving the transmitter and receiver, but putting the polarizer in between and then rotating it. Now here, we're going to have two successive effects take place. We're going to have the same effect that we had before, but now the polarizer is creating a factor of cosine squared theta. So if I rotate the polarizer by some angle theta, we're expecting the intensity of light that goes through the polarizer is going to be reduced by a factor of cosine theta. Now also the light that passes through is going to be tipped at an angle theta. So when that light reaches the transmitter, that's going to be an additional factor of cosine squared theta. So we'll have two successive effects of cosine squared theta. And so our theoretical value for rotating the polarizer, which is set up in the middle, would be the function cosine to the fourth. So one of these will be for setup number 1, cosine squared theta, and then the other graph would be a cosine to the fourth. So we'll have a data table for each one of those. It's probably going to be set at a peak of 50 units. We'll see what happens when we actually get this set up. We may not be able to keep it right at 50. It may come in a bit lower. Anyway, let's take a look and see what that setup is going to look like. All right, here we are set up at one of the tables. Here is the transmitter. The transmitter is plugged in. It's turned on. You can see that I've put a meter stick out here. There's no specific distance at which we have to do this set of measurements. So what I'm working from here is just, I just kind of move things back and forth until I got a pretty strong reading on my receiver. So I got the receiver set to 50. Now, I mentioned that we actually have an adjustment on this so we can kind of calibrate this to different values to start from. So I was able to get it to reach the value of 50. So that looks very likely like what we will go with. But that's what the setup looks like. Now, I found out about a 40 centimeter distance worked well, so that's what I've done. And now what we're ready to do is start rotating things, so let's try that. So I've decided to rotate the transmitter a little bit here. And you can see that on my phone, I've got out my level app. And oh, look, our table right there at least in the physics lab room. Who knew? It's level. So what I'm going to do is I'm going to get my phone, move it up here. I just measured it. Oh, no, it's coming in at 31. It was coming in at 30 before. This was going to be my example of 30. There we go. So that's a 30-degree measurement. Look at that, turned green. So that's at 30 degrees. And then over on this end, it looks like the intensity has dropped from 50-degree measurement down to, I'm going to call that, got to get rid of the parallax here. I'm going to call that 34. Okay, I'm going to have to go back and do more careful readings on this. That looks like 34 and a half, maybe 35, somewhere in terms of the intensity units. So that's it. We just continue to do 10-degree increments. All right, and I just thought it might be useful to go in and take a look at that 90-degree measurement. So at 90 degrees, are we actually going to see the intensity drop all the way down to 0? And I do have my phone on this, so this side is level. I realized I got to check both sides here, not just one. So I checked that. I checked the other side. That was level also, but it's been rotated 90 degrees. And that's pretty close. So it looks like the intensity, I would call that 0. So yeah, the polarization effect with these microwave generators is very pronounced. Anyway, I'm going to go back, do 10-degree increments, and put together that data table that we can work from. All right, here is the next setup. I've put the polarizer in place. Now notice the transmitter is, we said this is generating vertically polarized microwave light. And so what I've done is I've placed the polarizer so that it's only removing horizontal, of which there is none. And so I wanted to check and see if I could maintain 50 units for the receiver, and I've been able to do that. We'll see. I may stick with 50, or I may end up adjusting that, depending on what the rest of the experiment setup looks like. But that's kind of what it looks like. Now, what would happen if I take the polarizer and I rotate it? I'm going to rotate it by 90 just to see what an extreme 90-degree effect would be. And yeah, it went right back down to 0 again. So in this case, the receiver is aligned with the light coming out of the transmitter, but the presence of the polarizer in between is absorbing all of the vertically polarized light. Now, very quickly, I'm going to see if I can set up something that resembles 45. Ooh, I'm going to try this on the other. I don't have. Let me just try this. So, let me get this set up. That's just very roughly 45. See if I can get it to hold in place. I'm going to go back and be a little more careful. But what I'm seeing here is quite a pronounced drop. So this is down below 20 units. So is this a cosine to the fourth effect that we're seeing? And we'll see. I'll go back and again with this one too. I'll get those 10-degree increments of data, and then you guys can put together those theory curves and see how they match. All right, any questions at all, stop by office hours, and we can get whatever questions answered for the day.